So we're going to begin the next chapter. We've covered stuff on heat transfer and thermal heat and energy and loss of energy and modes of heat transfer. That was chapter 10. So we're going to finish up the year with a kind of a mix-up or a mashup of chapter 25 and 26 together. So we're going to do these two sections from 25, and then we'll jump to chapter 26 for two more sections, and that's it for the year. We're getting toward the end. These will be on your last test, obviously, those two main topics. And then during the next double, we're going to finally do that DC motor lab. Okay, so we'll spend the next double period just working on that. It's obviously not related to this, but it'll be something more interesting, I think. Yeah.
Will that be our last lab?
It will be our last lab, yeah, that's right. It'll be the last lab of the year. So we'll do three things. We're going to talk about the different models of the atom. We'll talk about what's called absorption spectra. And then finally, we'll talk about the atomic spectra with Bohr's model. So let's start with the beginning. First, for a long time, people supposed that atoms were simply just little white spheres. That's all they thought they were, like grains of sand. They would think of like a grain of sand, and you can't take a grain of sand and compact it anymore. The idea was that it's got to be a solid sphere, right? It's got to be a solid sphere. Like I can't take this desk and compact it anymore. It's pretty solid, right? So the idea was that atoms were solid, which makes sense. It's logical. And it turns out, we're going to see in the slides, that's not true, right? Atoms are not solid in most empty space, actually. But the atomic collection of these atoms together makes a solid structure. So the beginning idea made sense, because things were solid. If I wanted to hit through a wall, it didn't work, because the wall is solid. So you think atoms must be solid. It just makes sense in a logical nature. That was the beginning, okay? Then after that, we went to Thomson's model. And Thomson recognized, because of the electric charge of the atom, he did enough experiments to notice that the atom is electrically charged. And the only way to be electrically charged is to have separate positive and negative poles. So then Thomson said, you know what? We're thinking that there's just an abundance of positive charge and a couple of negative charges here and there. And the model for this for a long time was called a plum pudding model. You would never eat plum pudding anymore. Like that's like your grandma plum pudding, you know? But imagine, right? Imagine pudding, fig pudding. Sorry, fig pudding.
Is that what it is?
It's
plum.
Is it plum pudding?
Like fig pudding.
Yeah, imagine pudding with little things in it, right? Like imagine yogurt with granola for today nowadays, right? Okay, so you have yogurt and then a bunch of granola. Each little piece of granola that's in the yogurt when it's mixed is like an electron. Or what we call this now, actually, at least what I refer to it as when I teach, is the watermelon model. This is a watermelon, and the seeds are the negative electrons. Okay? Every other part, the entire mass of the watermelon is positively charged, but the seeds are little negative concentrations all over the place. This was also not true. Okay? But the idea led to the next type of model. Right? So we have to recognize that although these are not the right models in the beginning, they led to the next people saying, you know what, I don't believe you, I ought to test this more. And that's where, after Thomson, Rutherford came, and after Rutherford, Bohr came. So the progression of it is important. That's why we go through the history of this kind of stuff here, because this is really fundamental. So Rutherford came around and said, you know what, I'm going to test this out. And he did what was called the gold foil test. Does anybody know what the gold foil test was, or how it worked, or what it proved, or anything about it? Sarah?
It's like they shot away a piece of gold foil and some deflected at different angles.
So what did that tell us, Sarah? What was the result of that? Do you know what the conclusion they drew from that was? Oh, that's good, but you're on the right track. Yeah.
So it's a very small nucleus and everything else is like empty space.
So the idea, actually,
The density of the nucleus is like more dense than other parts.
yes. So the conclusion was that we have a very, very, very dense nucleus. Look at the middle, it's red. So that big Thomson model from the previous slide, that was pretty much all nucleus, with the electrons embedded in the nucleus also, was not right. You take that nucleus, shrink it down to very, very, very concentrated space, that's that red dot. And then the electrons are floating around. Didn't give much detail on the electrons in this model, but this model really helped us to recognize that the atom is mainly what? The atom is made up of mainly empty space. Empty space. And those rays, I think it was alpha or beta particles that were sent in the gold foil, the ones that did get deflected were hitting the nucleus. Why only a couple got deflected is because even if you have millions of atoms of gold, millions of atoms of gold, each of those atoms are very, very small. Those rays that you're bombarding with are very small. So a lot of them just pass right through. They found little open spots here, and here, and here, and here, and here, until a couple hit the nucleus, and those ones got deflected. And they were able to see the result of this on a viewing screen, okay? On a atomic spectrum screen, a viewing screen. All right, very good. All right, now before we get to the Bohr model, let's talk about what brought on the Bohr model. Let's talk about what brought on the Bohr model. So the atomic spectra are what really brought on the Bohr model. And the way I want you to think of atomic spectra are like a fingerprint. When you think of the fingerprints, your fingerprint is unique and it's different than Maria's fingerprint, which is different than Steve's, which is different than Rainey's. Now, you can get very, very close to perfect accuracy with fingerprints, almost 100% actually, especially when it comes to having like identical twins. But there are certain characteristics you'll learn. If you take forensic science next year, fingerprinting is one thing they talk about. It's kind of cool. There are like swirls and curls and these and bifurcations and little identifying factors. And just look at your fingerprint. Like look at it really close right now. It's incredible, right? It really is. It's unique to you. So that's the same concept that we're going to talk about here. It turned out this experiment was done where a certain amount of voltage was applied, potential difference, voltage, electricity, was applied to an atomic gas. So some of our atoms are naturally gases. Remember the noble gases on the right side of the periodic table? Those were all noble gases. They naturally occur in the gaseous state. So those gases were the ones that were originally tested. Now, if they were able to get hydrogen, helium gas very easily, they put it right in here. The voltage being applied to that gas got the electrons excited. The electrons literally were like, ooh, where's this energy coming from? I'm feeling really good, right? The electrons suddenly had energy. So what do the electrons do? When they gain energy, the electrons actually jump up to excited states. Shells, different valence shells. But when they return, they give off energy. So by spontaneously bombarding this with the amount of energy, it's giving off energy. Well, that's this light coming out. Now the light coming out is what was giving off. That light was passed through a single slit, so that physically only a small beam of light goes through, which then gets refracted in a prism. And what turned out, this is the amazing part, was that every single atom would produce a spectrum of colors that was unique to it. So if you had helium and hydrogen, compare the different spectra right here. I mean, look, this one has the first spectral line, this one only has one here. This one has spectral lines here, this one only has it here. It's missing this one. This one is similar, but then this is extra, it's not here. This is here, it's not here. So these atomic spectra, these little blueprints or fingerprints really, designate what kind of an atom you have. And there were similarities. You'll notice that certain materials, like this is mercury, hydrogen, mercury, and helium, all three have spectral lines that occur right here. And that's fine. But if you look at them in general, they're all different. They're all different. So the atomic spectrum was a fingerprint for it. Yeah?
So you see, like, those are all noble gases, right? So would this only apply to...
Mercury's not.
Oh, Mercury's not.
Mercury's
so
not.
would, like, noble gases have more similar... What you say?
There were definitely similarities amongst the periods and the families in the atomic spectrum. Absolutely. I don't know the exact details to which were which, but there absolutely are correlations. Just like certain things that go along there are metalloid or transition metals and stuff, there are definitely similarities amongst the different spectra that you can see. And yes, Wayne, sharing certain lines actually prove that.
Karen?
All right. Hold on 1 sec. Is my pencil low or is the battery low? Pencil's low. All right. We'll get back to it. Let me see if I want to add anything else. Well, this is interesting. This is a fun fact, more a little history. It's not something I'm going to test you on. But helium, believe it or not, was discovered as a new element by using the sun's light. By using the sun's light. Is it the sun apparently, I mean, what is there? Is there fusion or fission on the sun's surface? Which one is it?
Which one can we not do?
Yeah.
Wait, no, we can, no, but on Earth, I mean, no, it's fusion then.
it's fusion that's
Yeah,
occurring, right?
because whatever we can't do here is what
And helium's a byproduct of fusion, I think, right?
Is that high?
But anyway, helium is in the sun's light. So that was actually discovered using this, and that's where the word for it came from, helios. Helios means sun. That's where helium gets its name. That's it. It was just a fun fact. But besides that, math-wise, we want to go to the next piece. So with that said, let's take a look at the Bohr model for a little bit. This is where Bohr came up with this idea. Bohr, I don't know exactly if it was Bohr that was the person who did the testing for the atomic spectrum. A lot of the time, you guys know this, right? Scientists who are credited for work don't actually do the work. They come up with the conclusions then. So it's tough because, like, who was it? It was, who gets the credit for DNA? But it's not them. Who is it? Yeah, it was a female scientist in the group of three that did all the work, and then Watson and Crick took all the work and analyzed it and studied it and came up with the conclusion of DNA. But she was the one who actually did the work for it, yet because they coined it as in, like, patented in a sense, they are known as the ones who credit. Newton's a smart guy, don't get me wrong, but Newton's a thief. Newton took so much of his work from his students. So much of his work that is credited to Newton is credited because his students came up with the actual ideas, tested in labs, and then Newton came up with the theory. And said, oh, this is why it makes sense. Let me come up with a general theory for it. Anyhow, back to Bohr. So I don't know if Bohr did the atomic spectrum stuff, but Bohr saw what was going on and said, hey, something funky is happening here. Something funky is happening. And what he recognized was, he said, well, very much like the last model, like our Rutherford model in 1911, we're going to see that we have definitely a concentrated positive nucleus and those negative electrons on the outside, for sure. So he agreed. He absolutely agreed with Rutherford. But with Rutherford's model, Rutherford said the electrons are just anywhere. They're just anywhere. And Bohr said, I'm pretty sure there's something about the electrons where they are. And where they are in space from the nucleus, how far away, indicates the level of energy that the electrons have. And as they go further out, they gain electrical energy. But when they move down, they give off energy. And that's what we're seeing with the spectral lines. The spectral lines are exciting the electrons, and then when the electrons calm down, they've got all this extra energy, and they sit down. They got to release the energy somewhere, so they release it in the form of that light. And that's where the spectral line comes from. So Bohr kind of put two and two together. He took the idea and the lab experiment and came up with a real theory for it. So, again, his idea was that these electrons can cause spectral lines, but the spectral lines had specific locations that they occurred. So Bohr theorized, well, maybe it's just the electron jumping from one state to the next. So if an electron jumps from state 6 to 3, you get a certain line on the atomic spectrum. If it jumps from 4 to 2, you get a certain line. So those different indicating factors told him that they must be at discrete energy levels. Not somewhere random where they're just coming down or up, but specific locations. So electron shell 1, shell 2, shell 3, etc. And as it moves from shell to shell, it gains or loses energy. If it moves out, it gains energy. If it moves in, it loses energy. It gives off that energy. Right? So let's take a look at a diagram of this first, and then we'll jump into the formula. Let's look at a diagram first. So in this diagram here, we're going to see exactly what's happening. The electron is getting excited. It's getting excited by spontaneous emission. Okay, this happens to have, if you have some sort of energy that's bombarded on that electron. That electron itself then gets excited and jumps up from here, which is shell 1, to shell 2. Now, once spontaneous emission stops and they suddenly are no longer bombarding this with energy, that electron will drop back to where it belongs and give off its own energy as a result. The energy it gives off will have a certain wavelength and frequency, and that's where the math is going to come into play for this section. Okay, so let's take a look. Let's take a look at the equation for this now. And this is going to be the equation that we're going to utilize. So delta E equals HF. Delta E equals HF. Delta E is the change in energy of the electron when it moves from one state to the next. H is a constant. By the way, this is new. I didn't teach this last year, so it's not in your formula sheet. So if you want to open up your formula sheet real quick and add this information, that'd be a good idea. Okay? It's going to be on your test. I'll put it on the test. And you have regular formula sheet. But I would definitely make sure it's on your test and on the final formula itself. But this formula is new right here. We've been using that omega symbol for frequency. I'm going to use F here. I know I've used omega, but the book uses F, so I'm going to stick with that for now. Planck's constant is a constant, like the number 9.81, or any other constant on the bottom of that formula sheet. So maybe add that to the bottom of the formula sheet, and the formula itself goes on there.
We get constant.
Yeah, constant and formula. You don't have to memorize these. Okay, constant and formula. Now, this relates the frequency of the emitted wave to the amount of energy of the electron by what's called Planck's constant. This is called Planck's equation. This is called Planck's equation. Now, with that said, I want you guys to actually see what's happening mathematically. I kind of skipped one thing I want to mention because I think it's kind of cool. So I'll just point it out. Spontaneous emission, that phrase, is what's happening with the northern lights. With the northern lights. The photons that are coming from the sun, they get trapped in the Earth's magnetic field there, and they interact with the gas that's around it. So that color, the next color scheme you're seeing, right? The color scheme you see with the northern lights is really atomic spectrum. That's what it is. Okay, and you're like, oh, it's the beauty of nature. It's also just science, too, right? It's science. Because the magnetic poles of the Earth are stronger. Remember, when a magnet, where's the strongest? Down the middle of the magnet and the poles. As you go to the sides, those magnetic field lines get wider, right? And they're weaker over here. So at the north and south pole of the Earth is where you see the more concentrated values of photons, or whatever you would say. The concentrated energy of light. It's trapping the sun's photons physically because of the magnetism. But that's why it's at the poles, yeah. So let's take a look at this example first. We'll start with an example where we're talking about mercury, all right? An excited electron in mercury. It's real excited, okay? It drops from energy level 4 to energy level 2. From energy level 4 to energy level 2. If one electron volt is given a certain value, we'll talk about that in a minute, then let's go ahead and determine the frequency of the radiation. So first of all, let's start with this. Let me start with something right to begin. The way we draw this, and this is kind of odd. It's really kind of odd, and it was difficult to explain in the last class. I actually read up more online about this myself, because I'm still always learning about stuff. So here, the actual electron shells, okay, the actual electron shells themselves become less and less negative as you go out. You increase in value because they're becoming less and less negative, actually, which is a little bit interesting to think about. So, for example, this is E1, E2, E3, E4, each ring. And I told you a minute ago, as you go out further, you get more energy. But if you look at the numbers here, it would look a bit counterintuitive, right? It says that energy level 4 is this, and energy level 2 is this. But I just said to you a minute ago that as you get higher in energy level, you should get more energy, literally. But this looks like a number that's not as big as this number. Well, the whole idea is that you're becoming more and more and more and more positive, or less negative. Okay? So the first energy level will have the most negative number. So for example, this is not an atom. I'm just picking numbers. The first shell might have an energy level of negative 12 electron volts. The second shell might have an energy level of negative 9 electron volts. The third one will have an energy level of negative 15 electron volts. Negative 6 electron volts. I went the other direction. Negative 6 electron volts, or let's say 5 to be careful so we don't think it's proportional. So I want you to recognize that when you're at a higher level, how much energy the electron gains is the delta. The delta. The formula we wrote down was delta E. Delta E inside of absolute value on purpose. So tell me, between energy level 1 and energy level 3, how much energy does the electron gain? 12 and 5. How do they differ? They differ by 7, right? So it's literally gaining 7 electron volts when it goes to here. When the electron is no longer excited and comes back, it loses 7 electron volts. An electron volt is another unit for joule. It's another unit for energy. Okay, and we see the conversion factor in the problem. Again, an electron volt is a unit of energy. 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. Circled in yellow for you. Okay? It's a conversion factor. Also, on the bottom of the formula sheet, if you want to add that to the constants at the bottom, that conversion factor. 1 electron volt equals 1.6 times 10 to the negative 19 joules. So I want you to recognize what's happening in this problem. Okay? In this problem, we're going from energy level 4 to energy level 2. So what physically is going to happen here? Energy level 4 to 2. What's going to happen? It's going to lose, not electrons. The electron is the thing that's moving. The electron itself will lose energy. It's electron volts. They're not volts. It's not the same thing, actually. It will lose energy. So going from level 4 to level 2, causing it to lose energy, where's that energy going to go? It's getting emitted as radiation. And our question in this problem is, determine the frequency of the radiation emitted. So we're going to be looking for frequency. So we know already that here's our formula. Absolute value of delta E equals HF. That's going to be my formula. Now, I drew enough diagrams, so I'm going to scroll down a little bit so we can have a little room. So I'll start listing things, right? Oops. E4, given, E2, given, and Planck's constant, H, 6.63 times 10 to the negative 34. And it's a constant that you're good to know, but you don't have to remember this. And we'll solve for F. Now, can I just subtract these two? If I just subtract these two, is it going to work? And I'll give you a hint. Look at the units for H. Go back up a slide or two and look at the units for H. What are the units of H? Go ahead, Peter. Joules times seconds. So my energy unit is joules there. But what's my energy unit here? EV stands for, what do we say? What's the word? EV? Electron volts. Very good. Electron volts. So we cannot leave this in EV. We're going to have to convert it to joules using that yellow conversion factor. Okay, to convert to joules. But let's approach the problem first as if we're using this. So how do I find the difference between these numbers? I subtract them. Right? I subtract them. So let's go ahead and subtract those two numbers. I'm going to take the larger energy state, always, which in this case is negative 4.66. That's a bigger number than negative 5.43, right? Meaning more positive or less negative. So I'll do E4 minus E2 all over H. And that's what F is going to equal. So again, I'm just solving the equation for F. Solve the equation for F. This equation here becomes this one solved for F. What does delta mean? Delta means change from the fourth level to the second level. That's what's happening to the electron itself. I can subtract E4 minus E2 and get a number in electron volts, but I got to convert it before I divide by H. Okay, so let's go ahead and do that. What do we get when we do that? Negative 4.66 minus negative 5.43. What do you got? Yeah, which is positive. Yep, very good. Okay, and that will be over 6.63 times 10 to the negative 34 joules times seconds. That's H. So again, just look at your units. What should the units of frequency be? What should the units of frequency be? What's frequency measured in? Close. Not seconds. 1 over seconds, aka Hertz. Okay? So this unit of F needs to be in 1 over seconds. So theoretically, if I could cancel this and cancel this, I'm left with 1 over seconds as units. But these don't cancel each other. So you always got to convert your EV into joules. There's my conversion factor. Okay? Again, I'm just doing what we did in chapter 2, dimensional analysis. I'm changing my dimensions. I've got EV, I want to get rid of it. I've got 0.77 electron volts. So I put electron volts in the bottom. 1 electron volt is equal to this many joules. That was given in the problem. It's given on the formula sheet. So this is my conversion factor. I cancel electron volts, they're gone. So now I'm left with joules over joules times seconds. The joules will drop off, leaving seconds in the denominator. So I've got 0.77 times this. The 1 doesn't matter clearly. All over this number here. One sec. You have an answer? You want to? Yeah. Go. Okay, so again, 0.77 times 1.6 times 10 to the negative 19 is the number that's going to be in the numerator. What does that come out to be? What's 0.77 times 1.6 times 10 to the negative 19? Anybody got it? It's like 1.2 or something?
1.2 3
Uh-huh.
times 10 to the negative 19.
Okay. All over 6.63 times 10 to the negative 34. And again, this is in joules. This is in joules seconds. Joules cancel now, leaving me with just seconds in the denominator. Go ahead and use your calculator to do this. You will get a number that has a positive exponent because you're dividing by a number with a bigger negative exponent here. It should be on the order of 10 to the 15 or 10 to the 14 or something. Steve, what do you got?
1.85 times 10 to the 14.
86, if you round it properly. 1.86 times 10 to the 14 hertz. Okay, 10 to the 14 hertz. So for Mercury, this is Mercury, by the way, right? It's a Mercury in the beginning? Yeah, Mercury. So this Mercury atom actually would give off this frequency. It turns out that that's infrared. So you wouldn't even see it. But if you were physically there, you would feel the heat from the infrared wave. Maybe you wouldn't even see it to the human eye, at least you would see it. This is the process that we're going to undergo for all these types of problems. In a moment, we're going to start a second type of problem that's similar to this, very similar. But we're going to specifically look at hydrogen. And hydrogen has a very unique nature to it. Every atom has a unique nature, but we're going to really focus in on hydrogen for a little bit. Give it. So, next slide. What are you raising your hand? In the next slide, we're going to specifically look at energy for hydrogen. Right? Now, like we just said a minute ago, as you go further and further out, your number is going to get smaller in value, but it's going to become less and less negative. So as you go further out, you're increasing in energy. N is the amount of shells, or how many valence shells have gone out. So if you're at energy level 3, you put a 3 in for N. If you're at energy level 7, you put a 7 in for N. Oh, there should be a negative sign here. Correct this. Dang. I just wrote these notes. Put a negative sign out here, please. There should be a negative symbol there. Okay, put a negative symbol right here. So N is the energy level. So go out and calculate. What's E1? What's E1? The energy level at the first state. Thank you. Very good. Don't fall into the trap of actually using your calculator. What's E2? Who's got their math? Mental math.
Negative 27.6.
Where are you getting negative 27.6?
Multiplying by 2, right?
No, it's times 1 over that, right? Look at the fraction. It's negative 13.6, right? Times 1 over 2 squared. So 1/4 of that. What's 1/4 of 13.6? 3.4. The way I do it is 12 over 4 and then 1.6 over 4. 12 over 4 is 3, 1.6 over 4 is 0.4. And that's it. Anyway, what I want you to see, it's negative. What I want you to notice though, again, like I mentioned, is that as we keep increasing n, what's happening to the e values? As you keep increasing n, what happens to the e values? They become less and less negative. Good way to put it, Alex. Less negative. What number are they getting closer to, Alex? 0. Are they ever going to go above 0? Are they ever going to be positive? No. Look at the work. This is a negative quantity that's being multiplied by something squared, which is always positive. Even if I make n negative, squaring is still positive. So this is going to get closer and closer and closer and closer to 0 as n gets larger. So I can say this. Okay? As n gets larger and larger and larger, the energy state gets closer and closer and closer to 0. 0, believe it or not, being the highest energy state. Because remember, the energy state is the difference between where it started and where it ended. So if I start at the regular level, which Steve told us was 13.6, negative 13.6, right? So follow me please, right? I'm here at negative 13.6, and then I suddenly go all the way up to 0. It means that an electron, I gain 13.6 electron volts. If I start at negative 13.6, and I go from E1 to E2, find the difference between these. That'll give us 10.2 electron volts, jumping from here to here. So depending upon where I jump from, I will get to a less negative energy level as the amount of shells gets further and further and further away from the actual nucleus. Okay? So we're going to use this formula. This formula is for hydrogen. Let me point this out. Give yourself a little note here. If you had a different atom, this is what would change right here. This number. So for hydrogen, the number is 13.6. That's called the ground state. The ground state when n equals 1. Right, the one that we did. The ground state of hydrogen is negative 13.6. The ground state of other atoms are different numbers, but they follow the same idea. Multiplying by 1 over n squared. 1 over n squared. Where n is the energy level. So let's take a look at mathematical here. This will be given in the problem, so you don't have to memorize this. Okay? Is that clear? That'll be given to you as an example of this, so we can see it. An excited electron in a hydrogen atom drops from energy level 6 to energy level 3. So it's going to be energy level 6 minus energy level 3 equals HF. Again, my formula being this. But the problem here is that I don't know E6 or E3. I don't know H either. H is a constant. I don't know F either. So I need to calculate E3 and E6 first. In the previous example, in example number 1 with mercury, I told you the energy level was like 5.33 or 4.6, whatever they were, right? Here, because it's hydrogen, because I'm giving you this value, you have to be able to calculate these energy levels. And I will give you that number, 13.6, that formula from the previous value. So let's go ahead and apply it though. So to get energy level 3 and energy level 6, negative 13.6 times 1 over 3 squared, so pretty much a ninth of that, and negative 13.6 times 1 over 6 squared, so a 36th of that number. Can you give me some numbers for these, please? Alex, what do you got for me?
Negative 1.5.
Okay, and the other one? Green?
Negative
0.38. Okay. And my units are electron volts. Those both sound like reasonable numbers. And again, look at what happened. As you go from energy level 3 to energy level 6, you gain energy. You go from being a very negative number to not as negative of a number. Which means you're starting, think about the y-axis please. Start on the y-axis at negative 1.5 and then move to negative 0.38. That means you're moving up, doesn't it? On the y-axis, you're moving up. You're increasing energy when you go from 3 to 6. So the electron now has a lot of energy at state 6. But it's going to drop back down. And what is it going to do with that energy? It's going to give it off in the form of radiation. So we're going to take a look at dropping from 6 down to 3, which is why we're going to subtract these two numbers here. So let's go back to our formula and use it. So I've got negative 0.38 minus a negative 1.5. A lot of double negatives occurring here, you'll notice. Okay, please don't let them confuse you. A double negative means positive. So we'll get energy level difference of what? What's that difference going to be? What does that turn out to be? 4.3 minus 3, 1.3. 1.13-ish? 1.2? Did you? Oh, because the rounding probably, yeah. So we get 1.12. And remember, h is Planck's constant. So I've got my energy level change. When I went from energy level 6 to energy level 3, gives me this number. I take this number. Can I divide it by this right now? Can I divide this number by this? And is it going to work right now? Why not, Sarah? That's,
It's not in joules yet.
yeah, we got to convert this to joules, so when we divide by joules seconds, the joules cancel. So let's go ahead and multiply the left-hand side of the equation by the conversion factor of 1.6 times 10 to the negative 19 joules for every 1 electron volt. I can cancel electron volts as units now. I can cancel electron volts as units now. On the left-hand side, 1.12 times 1.6 times 10 to the negative 19 equals, what is this all going to become on the left-hand side? Give me what it becomes on the left-hand side. So we're doing this number here, times this number here to get the numerator, and then we'll divide by this whole thing. So that can go in the denominator already. The denominator already can read this. Alex, you got it?
It's 1.792 times 10 to the negative 19.
Very good. And now I can cancel joules for joules. Yes?
I'm kind of confused how you keep playing this thing in orange over here. Like, I get like why you're doing it.
This right here?
Yeah.
Yeah, because electron volts are a new unit. We've never learned them before. So energy, we measure in joules, right? But then we also talked about energy can be measured in calories. Remember last unit? Electron volt is a new unit for energy. When you're talking about small units of energy, you use what are called electron volts. Now, 1 electron volt is a very fundamentally small unit of joule. Because this constant is in joules times seconds, we need joules to cancel. Because this is going to be then electron volts over joules. They don't cancel. And you need to get 1 over second as an answer. Now the units here are left with 1 over seconds, which is hertz. So it's just dimensional analysis. That's all it is.
So you can't figure it out leaving it in electron volts.
No, you can't use the electron volts in your calculation. You have to convert it to joules every time. Every time. Yes. Yeah. Okay, so I take 1.79 times 10 to the 19 over this. I get some math in here, not like heavy math. It's one formula, right? E equals HF, or delta E equals HF. And then you got to know how to calculate E1, E2, E3, E4, like you just did in these problems, by using this, this number times 1 over n squared. And this will be given. This formula will be given on your actual test. Okay, I gave you 3 homework problems for this to practice. Please make sure to get to them tonight. Your 10.3, 10.4 was due today, so I hope you turned that in online. If not, I got a couple hard copies from some of you guys. Do you want to ask any questions about that from yesterday? I left early yesterday, remember, for the game. Did most people get it? Were there any concerns, any problems, any questions you wanted to propose?
You actually,
Yeah. On the homework? Sure.
this number 36, just like had a little bit of trouble, I guess, setting it up. Because like,
Does it have to do with copper going into water or lead going into water?
probably, yeah. I think so. Yeah, exactly. Yeah, that one.
So when that happens, you assume that the system is closed and the energy lost by the lead will go into the water,
Okay.
which is what allows you to say that the Q from one will equal the Q from the other.
Right.
That's where that equation comes from right there.
Yeah.
Then once you have this equation, I think it asks you to find the equilibrium temperature.
Yeah.
So if you can hold this for a second. So delta T is final minus initial. But both of them are going to come to the same final temperature because it's equilibrium. So the TF for the copper or the lead and the TF for the water are both just TF, the same thing. You knew the initial temperature for both.
Right.
You knew the mass of both.
Right.
You have the C value in tables for both. So it's a matter of solving for TF, which appears on both sides of the equation. So you have to do some distribution and moving things around to solve.
Okay.
I would look at the first example we did in class from 10.3, 10.4. That's where that one comes from.
Okay. Should I?
I'm going to check you off for homework.
Okay.
Don't worry. I got you. Yep. Just for you to practice.
Yeah.
I did. How much time do you have left? Is it like a minute? I'll show you tomorrow. I did have a little. Remember the little heat transfer demo that we had? I had like a little Georgia before. I remember we did. What did you say? Something about town. What does that have to do with what I just said?
That's so lucky.
I'll bring my laptop.
Oh, wait, no. Oh, that's marker.
Wait, actually, I feel like it's gonna hit someone.
Good.
I don't want to.
Emily, cover your face.
Ooh!
Left hand. I require the ball. I require the ball.
Hey, your project deadline is fast approaching. Your next test is next Thursday. So please, if you haven't started that project yet, God forbid you haven't started building it yet, you better get on it right away. God forbid.
That really was. I'm so. This so man. Yeah, man.
Happens to me every week, please. I'm always in the wrong day in my head. Maria, did you submit the lab?
Yeah.
Okay, I didn't grade it yet, that's why. So it's not going to include this. It'll include the test, though. Okay?
Yeah, that was wrong.
81 the test. Because your last, your last test you got a 30.5. This test you got a 28.5. So that's not much of a lower grade. So it's not going to bring down your grade as much.
Oh, really?
Really?
Oh, wow.
Okay, but I got to grade your lab still, and then I'll give you more of an update. Guys, have a good day. Enjoy your day. I have your charger. Thank you very much, sir. I appreciate it. You too, Alex.